You've come to the right place if you want to learn even some more derivatives. Okay, like what else can we do the derivative of? Well, I'm glad you asked. How about the derivative of a log? The derivative of ln. How about the derivative of a log? The derivative of ln. ln tends to get a bad rap. It's always at the end of the year. You never get to it, or if you did get to it, again, you were thinking about summer vacation. But ln is just a function. Okay, a function is that whole idea of I input, I output. I think we all understand that if you input into e to the x, your output is exponential. You know, it gets really big really quickly. Well, if you input into ln of x, it's the inverse. The ln of x is the inverse. All I'm trying to just sell you on here is that it also is a function. It's a function that has slope. And of course, if it has slope, it has a derivative. Are you trying to understand a little bit more about calculus than just getting answers? Do you understand, like if I asked you what you notice about this slope, do you notice that the slope is very, but it also very quickly becomes very, so we have a derivative that somehow has to have some big slopes, but eventually it approaches a slope of 0. Now, it's never going to be a slope of 0, but it approaches that slope. What kind of formula is going to do that? Now, I don't expect you to kind of just whip that out, but let me show you a little math. If you consider, as it says up here, if you consider y equals the ln of x, algebra would say that that would be the same thing as considering. Now, what I just did right there is a little trick out of the algebra bag. I based both sides. I don't mind talking about that again if you're like, ooh, I don't remember that. You're just taking the base, e, and you're transferring it over to the other side. You're just rewriting the equation as a base e to the y power. But why would I want to do that? Why would I want to do that algebra move? What are we trying to do again? We're trying to find the derivative. Okay. Anybody know how to do the derivative of ln? Well, no. That's why we're talking. Anyone know how to do the derivative of e to the y? Ooh, the derivative of e to the y? I remember that from yesterday. That's going to be, let's draw the sort of algebra calculus line. When you look back at your notes, above the line is algebra, below the line is calculus. Now, I'm actually a little nervous here. Maybe I didn't do a good job of teaching it. What's the derivative of e to the y? It's going to be the same. It's going to be the same. Listen, e to the is always the same. You say, but Miss Naylor, it's a y. Yesterday was an x. Don't you have to do the derivative of the inside? Don't you have to do the derivative of the exponent? What's the derivative of y? Now, when you figure it out, when you get to the point where you're like, I understand math, when you figure it out, you start using rules, and maybe you're not aware of that you're using them. What we just did right there was called implicit. I'm not going to make you write an essay about implicit, but implicit just means that you're doing the derivative when y is like inside the equation. So, hey, no biggie. We did the derivative of e to the y. I wrote down the same thing. We did the derivative of the exponent, the inside. We got dy dx. Don't forget about the derivative of x. So we get dy dx equals 1 over e to the y. We get dy dx equals 1 over e to the y. Why is that even ringing? How does an iPad ring? What the? A switch?
Have a switch on the left side. Where the volume button?
Nope. Just has this switch on the top. So I guess what I'm going to do. Turn that thing off. I have no idea what that's doing. Figuratively, candy bar for the first person that answers this. Figuratively, because I actually don't have any candy. What's e to the y equal? What's e to the y equal? Candy bar. X. What? Say what? Wait. What? The derivative is 1 over x? Yes. The derivative is 1 over x. What's that mean? What's that mean? What kind of slope do you get when you have a small number, a small x value? What kind of slope do you get when you plug a small number into that equation? You get a big slope, right? 1 divided by a small number is big. What kind of slope do you get when you plug in a big number into that equation? When you plug a big number in? A small slope that approaches 0. 1 over x. What's 1 over x? It's the derivative of ln of x. 1 over x, the derivative of the ln of x. Now, maybe you already wrote that down. I just want to make sure you realize that that's like our conclusion. So the derivative of ln is 1 over x. The derivative of ln is 1 over x. And it's kind of cool because I know I just showed you something over here, but I mean, if you go to your favorite x value, maybe x equals 7, like it only takes 2.5 seconds to figure out the slope at x equals 7. It's 1 over 7. So we could do this all day long. The slope is always going to be the reciprocal. It's always going to be the reciprocal. Okay? Now, we can take this reciprocal formula and we can kind of unize it. And we can put the letter u in here. It's still 1 over u. Don't forget the du dx. So we have 1 over u du dx. Now, if it doesn't dawn on you, like during today's lesson, it will probably dawn on you soon that we're creating quite a bit of rules. I'm actually going to help you organize them on Monday. I'll give you a suggestion on like a way to simply organize the rules. But it's your notes right now. Put a box around it. Make sure that you highlight it. It's another rule. And we're not done yet with this rule because we've got some interesting observations when we start doing some actual problems. So we've got this rule. It says 1 over u du dx. Here's an obvious ln equation. When the problem's written like this, as I sometimes say, I hate to say assume. So we're going to say the word that you would know. You would know that it's x that's to the third power. When the problem's written the way I wrote on the board without parentheses, you would know that it's inside like that. So let's do the derivative of ln. That's 1 over the inside left alone. 1 over the inside left alone. Times the derivative of the inside. That's that whole chain rule. It seems to show up a lot. So we get 1 over x cubed times 3x squared. Upon further inspection, 1 over x cubed times 3x squared is going to have some canceling. And look what you get. You get something over x. In this case, 3 over x. Seems like it kind of went back to the original rule. Again, that reciprocal idea. You'll see what I'm trying to show you here, but let me help you see. Now, the way I wrote that problem down, you would need those parentheses. Like, I put the parentheses there because purposely this is a different question. This is the ln of x, the whole thing cubed. Okay, so again, the parentheses come with the problem. Now, I know you're excited about our new rule. At least pretend that you are. But what's kind of the roadmap for this problem? What's kind of the guide for the derivative? What's on the outside that you see? So good. We got a chain rule. We got something on the outside. We've got something on the inside. Okay, so make sure that you do the chain rule. Make sure you leave the inside alone. And then do the derivative of the inside. Now, the derivative of the inside is 1 over x. Well, would you take a look? Our derivative is something over x. In this case, it's 3 ln of x squared over x, but it's something over x. Let's see if we can kind of foil the math here. In other words, can we like make it not work? What do you mean make it not work? I mean, like, is our answer always going to have an x in the denominator? Well, here, I mean, certainly this won't work. I mean, we've got a 2 over x squared. You know, it's going to have to like mess up. It's going to have to be upside down. So we got the ln of 2 over x squared. All right, now if you didn't think or have a hunch that I'm trying to prove something here, you just do the derivative. What do you mean just do the derivative? Well, I hope you do the derivative of ln and you follow the rule. The rule is 1 over u. So 1 over 2 over x squared. We'll have to clean that up, but that's 1 over u. Now the derivative of the inside has to get chained on here. That's not like one of those PAL clouds from like your favorite comic book. That's not like PAL. That's what? That's 2x to the negative 2. So that you can do the derivative and get negative 4 over x cubed. Are we ready to kind of switch to that? You guys should be subtracting and getting a negative 3. But I'm ready to put that negative 3 down in the bottom. Are you? Multiply the tops, get negative 4. Multiply the bottoms, the denominator. Oh, wait a minute. Multiply the denominator. Okay, now 2 is going to multiply over here, and of course x squared is going to multiply over, but we can cross, oh my gosh, we can cross off, and we end up with, we end up with something over x. Geez, I guess the derivative of an ln is going to be 1 over x. Okay, or negative 2 over x, or 3 over x, or even in this case, some kind of log squared over x. Okay, interesting. When you do the slope of a log, it's a reciprocal, because if you go way out to the right, your slope is going to approach 0. One more derivative. Do we have time? Yeah, we're good. One more derivative. This one I'm not going to like prove to you, but you'll probably, oh, what's that? I'm going to skip that. Let's just look at it. I don't think we have to do the problem, but sometimes, well, not sometimes, but just about every time we find an equation, remember, by plugging in. I guess we could. I'll tell you what. Let's not skip it. I shouldn't have said that. Let's do that little extra equation here. I'm going to strike that comment. Let's not skip that. I want to make sure you guys are good with this concept, but you should say quickly that, okay, that's the same thing we've done for every derivative. So it was meant to tie into the previous problem, and so we've got this point. Okay, now that point's not just like completely random. That would be a point that's actually on this graph. That'd be a point that's on this graph. But the good thing is that it's got an x value, and we can plug in to our little derivative here. It's actually quite a simple derivative. It's just -2 over x, so -2 over 1, because I've got a nice little slope of -2. And then, of course, your equation is y equals mx plus b. I actually wanted to graph this, so again, let's not skip this problem. I want to make sure you understand that when we get our y-intercept, ln of 4 plus 2, when we get our equation, you wouldn't have to put parentheses around that, but shoot, I just realized something. I could fool you and not tell you this, but I made a little mistake. There's nothing wrong with the math, but this point does not actually fit with this equation. Okay, this equation, if I was going to plug in the number 1, I would actually get the ln of 2, not the ln of 4. Let's fix it. That's kind of my bad there. It should be the ln of 2. It's just going to change in here. I just wanted to show you this. I know some of these graphs are new to you guys, but here's an ln graph, even though it's the ln of 4 over x squared. And here's my hopeful tangent graph. Don't do something silly like add those 2's to get 4. It's the ln of 2 plus 2. The ln of 2 is a whole different number. Okay, but with a little bit of cleanup on the window, we can kind of make this do what we want it to do. Here comes the ln graph. And, uh-oh, what happened? It's not tangent. There's something I'm missing here. So this isn't like part of the script. This is not tangent. It's supposed to be touching. Anybody see anything? 1, -2.
No, it's 4.
All right. Take a look again. That's better. All right. So this whole thing about tangent lines, it still works, even though we're getting into these crazy rules, these crazy derivatives. Okay. I actually do have one more derivative. So I appreciate your attention. But I always like to show this last one because on Monday, we're going to organize these rules a little bit. Try not to let this blow you away. It's actually the same thing with one adjustment. So we're doing the derivative of we call it a general log. Now, a general log is not specifically a natural log. It's not specifically an ln. But look, it's still 1 over u. It's still the reciprocal. It's 1 over. All right. There's honestly just one adjustment. It's that we also have to divide by the ln of a. We have to divide by the ln of the base. Kind of like our adjustment from yesterday for that exponential. All right, now I know it's kind of a long week. It's a long period. Just try to stay focused a few more minutes here. I want you to be able to leave saying, okay, I'm just following a rule, but let's follow it. So I have the log of 9x to the 6. Log base 9. The log base 9 of x to the 6. The main theme of this rule is that it's 1 over. Promise, it's 1 over. Now, if you're like, 1 over what? 1 over the inside. The inside would be the whole x6. So 1 over x to the 6. Don't need to change anything. Don't really need to even think about anything except just plugging in to 1 over. Now, you do have to do a little thinking now because it's a base 9. Base 9 requires us to kind of like adjust the slope by a ln of 9, except what I'm really doing there is dividing by the ln of 9. And then multiply by the derivative of the inside. And then okay, I still get 1 over x. Actually, it's 6 over x. And it's also over ln of 9. But look, I end up with an x in the denominator. Okay, so it even works for like a general log. I just noticed something in my notes, and you guys are going to ask when you look in the solution manual. So one other little thing here today. The ln of 9, what you should have learned in algebra, is that that's the same as the ln of 3 squared. Okay, now, honestly, we all know that 9 is 3 squared, but why would I think of it as the ln of 3 squared? Well, something else from algebra is that the coefficient the power comes down as a coefficient. Now, what's that? Students will ask if you're still like on board here. That's not the derivative. That's a rule from logs. A log always makes an exponent come down in front. But what I'm saying here is that we now have a 2 ln of 3, which is able to interact with this 6. If you're the kind of student that's like, am I going to have to do that on a test? Okay, no. But it's going to show up at least one time in the assignment. I don't want you to think that things are just magical. Maybe it seems magical, but an exponent is able to come out front. It's a property of a log. And then I can divide those coefficients. All right. That I would think is enough for today. I hope to see you next time.